All right, in this video, we're going to look at how to find complex roots. And if you guys recall, a complex number is a number that has a real portion and an imaginary portion. So it can be written as a plus bi. And so when we find our complex roots, we're looking for roots that are not truly there. They're going to have I in them, which means if you guys recall, the I comes from square rooting a negative number. And so we're actually going to be using the quadratic formula again to be able to find these. So first, we're going to go ahead and look at this equation. The degree of this polynomial is 4. So if we want to know the degree and it is written in standard form, we look for the highest exponent. If it's written as a linear factorization, that's when it has all the parentheses. That's when we add the exponents together. So since this one is in standard form, we just look for the highest exponent. That means that it should have 4 roots. So remember, root is another word for x-intercept. It's another word for if you want to find the solution. So if I asked you how many x-intercepts would this graph have, potentially I would guess that maybe it would have 4. If I said how many solutions could I find for x, I would say 4. If they asked me how many zeros the graph had, remember that's when the y-coordinate of the function equals 0, which is another x-intercept. So those are all synonyms for the word root. All right, so we're going to go ahead and draw a sketch of the graph. So first I have to graph it on my calculator. I'm going to go ahead and clear my calculator. So I've got x to the 4th plus 2x to the 3rd minus 11x squared plus 8x minus 60. And so here's my graph. Now, once we do these after what I'm about to show you, we will actually use this screen. I can't see very much of the graph. If you guys recall, when we were sketching these ourselves, we had no y-axis, and on the problems that did have a y-axis, it was in like the several hundreds because these graphs are very stretched. So I can't see everything I want to see right now. In future problems, that will be fine, but I want you guys to kind of understand what we're doing. So what we're going to do is we're going to hit the window button, and we're going to change it so that the y minimum is negative 200, and the y maximum is positive 200. So we're leaving the x's the same. We're just really stretching out that y-axis so that we can see it. So what I'm going to do is just draw a little sketch of this. Something like that. Okay. And then if we look at this picture, I can see 1, 2, 3, 4, 5. It looks like it's at negative 5. I will double check that in a moment. And then 1, 2, 3. Okay. So if I want to double check and see where the x-intercepts are, I can go ahead and hit y equals, go down to y2 and make my y2 0. And then to find that I can do second trace, find the intersection. There's my 3, 0. And then my other intersection, I just have to move it closer to the other one. Found the same one. I hopped over to the other line so I could do a better job. Okay. So negative 5. Remember, this is the calculator saying 0, but kind of having a hard time. This is scientific notation. So the x-intercepts are negative 5 and 3. And if you look at this, we have x-intercepts at 5. We've got y equals x plus 5, right? That would be our linear factorization form. And when I look at this, it looks like they go straight through and straight through. So that's multiplicity of 1, multiplicity of 1. Now, I know that the degree is supposed to be 4. But so far, based on what I know about sketching graphs, this is only a degree of 2. So I know that I have x equals negative 5, multiplicity of 1, x equals 3, multiplicity of 1. And so that means that the rest of the roots must be complex. They don't show up on the graph. That means they must be imaginary. All right, so what we're going to do is we're going to go ahead and finish this problem, and this is how we do it. We're going to take the equation, and we're going to divide it by the factors that we already have. So I'm going to take x to the fourth plus 2x to the third minus x to the minus 11x squared plus 8x minus 60. We're going to divide it by x plus 5. And we're going to divide it by x minus 3. And then when we get the result of that, then we will have the rest of the factors for the equation. So I'm going to go ahead and use synthetic division because these are simple factors. So I'm going to say -5. It does not matter which one you do first. And these are actual factors, and so that means that my remainder has to be 0. These are factors of the equation. That means the remainder has to be 0. I know that because if I plug in -5, I'm going to get 0 as a result. If I plug in 3, I'm going to get 0 as a result, right? That's why they're x-intercepts. And if you guys remember, the remainder theorem says that when I plug in the number, the answer that I get as a remainder is the same as if I was to evaluate the function. So if the function is written as f of x, then f of -5 is 0, f of 3 is 0. So I know that this has to be 0 here. All right, so I'll do my synthetic division. 15 for -20, -12, +60. Okay, so when I did that first set of division with the first factor, I got x to the third, so I'm dropping it by 1. X to the third minus 3x squared plus 4x minus 12. And I'm going to go ahead and take that, and I'm going to divide that by x minus 3. So now I've got 3, 1, -3, 4, -12. Again, it's a factor, so I know my remainder has to be 0. So that's 3, 0, 4, 12. Okay, and then I'll drop it by 1, so I've got x squared plus 0x plus 4. Okay, so I'm going to go up here and I'm going to finish writing the equation. So that means that I've got x squared plus 4. I'm going to go ahead and leave that 0 term out that was in the middle. So this right here is the standard form. This right here is the form that is not quite linear factorizations, but close. I'm going to put linear in. So this is a linear factorization. This is a linear factorization. This is factored, but it's not linear. It's x squared. But these are the factors of the graph. So these equations are the same. So we know that if we have an equation that's written in factored form, all we have to do is say, okay, my x-intercepts are -5 and +3. But with this one, I have to set it equal to 0 to solve for those x-intercepts. And when I do it, I'm going to get imaginary answers. So let's go ahead and do this problem real quick. The next one you can go ahead and cross out. We're going to have to do that one on the back side of the page. So here I'm going to go ahead and just say that I need to take x squared plus 4 and set it equal to 0, and that's because I have this as a factor up here, and I'm trying to find out what the solutions are. So I'm setting it equal to 0. Now, we have two options for doing this. We can do kind of the easy route, which is just to recognize that we can subtract the 4 over. X squared equals -4. And then we can square root both sides, and we get x is positive or negative square root of -4. And we can say, okay, that's a negative, so let me put an I in the front. And then the square root of 4 is 2, so this is x equals plus minus 2i. So that's one option. The other option is maybe not to recognize that that was a simple way to do it, and then just do the quadratic formula. So if we were to do the quadratic formula, then we would say negative b plus or minus b squared minus 4 times a times c all divided by 2a. Is this the quick way to do it? No, but this might be the only way you saw to do it if you're not paying close attention. So that's 0, so I'm not even going to write it. So here I've got 0 squared minus 4 times a times c. I am not going to plug the square root in my calculator because I know I would get an error message if I did. This is going to be a complex number, which means it's going to have a negative underneath the square root. So I'm square rooting negative 16. I'll go ahead and make that a positive and stick the I in the front. So that means this is plus or minus 4i over 2. Which is plus or minus 2i. So if I wanted to know all of the roots, real and imaginary, so real and complex for this problem, I would say that I have an x-intercept of negative 5 and positive 3, and then I also have imaginary roots at 2i and negative 2i. So when I predicted that I would have 4 answers in the beginning, I was right. I do have 4. 2 of them are real, 2 of them are complex. So don't worry about this second example right now for the video. We will do that one tomorrow in class.